Hi and welcome to the University of New South Wales and in particular the School of Mathematics and Statistics. My name is Thomas Britz and I'll be looking at the problem number 37 from the course MATH3411. This problem is about Markov chains and using them to encode Huffman codes. The basic premise is that if you have some message, then the symbols, which might be, for instance, S1, S2 and S3, for instance, they might not be occurring independently of each other. In fact, in this scenario here, if you, for instance, get S1 as a symbol in your message, then the assumption in this setup here is that there's a 0.7 chance of then getting another S1, the 0.2 probability of getting a S2, and finally 0.1 probability of getting S3 right after that S1. So unlike in the extension, the source extension scenario which we're looking at, assuming that there was independence of occurrence of symbols, here we're not assuming that. And in general, why should you assume it? If we're talking about languages, for instance, the English language, for instance, if we have a Q, then almost always we'll have a U coming straight after it. That U will have high probability given the Q, whereas QS, for instance, has very low probability. So the probability of an S occurring right after a Q would be very low. Here we have the probability of, for instance, S1 occurring right after S1. That's rather high. Whereas, for instance, S3 occurring right after S1 is very low. So this is the setup. That gives us a lot more information, and we can use that information to form nicely compressed codes. One thing that we need first is an equilibrium probability distribution, and that's given there. And in this exercise we have to find that by finding an eigenvector to the eigenvalue 1. Because we have that m times p is equal to p, because p is an equilibrium distribution. So this is an eigenvector corresponding to the eigenvalue 1 of m, and it has more properties than that. It also is a probability distribution, so if you look at the sum of these entries, 6 plus 7 plus 4, and these are all 17ths, then that adds up to 1. So this is a particular eigenvector here. It's the particular eigenvector that is scaled to 1. Now, if you were in a test or exam, a typical situation is that you don't have to find the eigenvector, it'll be given to you, like here, and you just have to describe why it is an equilibrium probability vector, in which case you just show that m times p is indeed equal to p, and you have that the sum of these entries is in fact equal to 1. And we see that that is true. These two facts together give us that it's an equilibrium vector and it's a probability vector as well. So it's the equilibrium probability distribution vector. Okay, now let's use this setup to find some Huffman codes. And we have 4 probability distributions right here. We've got this one and these 3 here. So for each of those, we'll find a Huffman code, and then we'll use it to encode stuff. So let's do that. So first of all, we have the Huffman code arising from the probability distribution there, from the equilibrium there. So we have S1, S2, and S3. We have to encode each of these. So we do that just by looking at these 3 probabilities. There's one little thing though. Here this is S1, S2, S3. When we perform the Huffman encoding, we have to take care that the probabilities are in non-increasing order. So here they are increasing, so we have to swap them around by swapping the first two symbols around. So if we quickly do that, we have S2 with probability 7/16. The probability of S1 is 6/16. And then we have S3, 4/16. And then we just perform the Huffman algorithm on these. 6 and 4 is 10. And then we combine these and we get 1, and we're done. Now we just have to go backwards in the splitting up phase. So we have 0, 1, 0, 1, and we get 1 there, and 0, 0, and 0, 1. Okay, now we have the first code here. S1 was encoded by 0, 0, S2 by just 1, and then we have 0, 1 there. We continue to do that for all 4 codes, so we've done 1. We also need Huff 1, 2 and 3 by looking at these, and I'll do that right now. I've now found the 4 Huffman codes corresponding to this probability distribution and also these 3. So Huff E, Huff 1 to 3, and we're asked to encode this message, S2211233. Now what we're going to be doing here is using each of these symbols to determine how the next symbol will be encoded. So right at the beginning we have S2 there. It doesn't have a prior symbol, any symbol before it, so we're just going to be using the equilibrium Huffman code there. But after that, then we'll be using one of these 3 according to the sequence of these symbols. So let's write down these symbols on top of each other like this. S2, sorry. S2, S1, S1, S2, and 2 lots of S3. So the Huff code, the Huffman code that will be used for these is first the equilibrium code, and then it'll be the second code, Huffman code, to encode S2 here, because we had S2 just before it. To encode S1, we'll be using the second Huffman code because there's S2 right there, and let's just write this down. So we've got 1, 1, 1, 1, 2, 2, 2, if you can still read that, there we go. And finally, to encode the last symbol, we use the third Huffman code because we have the third symbol just before it. So now we know which codes to use. Now we can just go and use them. So let's do that. So for S2, we look at the Huffman equilibrium code. There we just have a single 1. For the next S2, then we go to Huff E, and that's 0. Then for S1, well, that's in the same code. S1 again, but now we have to go to the Huffman code number 1, and S2 in that code as well. And then we have S3 in the second code. That's 1, 1. And then we have S3 in the third one, which is a single 1. And we have a sequence of bits there, which encode this message here as follows. So 1, 0, 1, 0, 0, 1, 0, 1, 1, 1. If we just write these down in order, and there's our code word. And we're done. Now a natural thing to ask is, how good is this? Is this a good encoding, or have we compressed our encoding as much as possible? And let's have a look at this specific message. Here we have 7 symbols and 10 digits. So that's per symbol, it's 10 sevenths, or roughly around about 1.4 something for 1 or 2. So that's just a number. And is it a good number or a bad number? Well, think of if we're to do it with a block code, where we're taking these three symbols, S1, 2, 3, and trying to represent in terms of a string of just ones and zeros, or zeros and ones, of equal length, then we'd have to use the four codes 0, 0, 0, 1, 1, 0, and 1, 1. So on average, we'd be using 2 bits per symbol. So this is certainly less than that. So that's not too bad. It's actually almost 2/3 of the just straightforward block coding. Let's have a look at how good it is actually just compared to using a single distribution. So for that, we have to look at the average code word lengths of each of these. And when I was constructing these codes, it was rather easy to see that the average lengths were 27/16 and 1.3 and 1.4 and 1.5. So this is about 1.59 apparently. So the average length here of the equilibrium is bigger than each of these more fine-tuned code word lengths. So we do get some nice compressions, especially 1.3 is significantly better than 1.59. So on average, if you're to look at what the Huffman code can do in terms of lengths, we get the average length for the Huffman code LM, or for the Markov chain here, to be, well, the weighted average of these lengths. So this length, given by the probability that we did get symbol 1, so 6/17 times L1 plus 7/17 times L2 plus 4/17 of L3, and then we get some number, which I think I've got right here, was 1.39, and that is really good compared to 1.59, and in particular, it's almost 2/3 of the block code length. So this is actually quite good. So that's the number of digits needed on average to represent each of these symbols in a message, given these dependencies. Okay, thank you very much.